Hello, we are Group 7. Our topic is about adversarial attack on graph convolutional network. First, let me introduce some basic concepts. Adversarial attack. Today's neural network can achieve a state-of-art result, but it's fragile. Neural networks are constructed by stacking neurons layer by layer, but it's the black box model. We can't exactly tell the meaning of the numbers in each layer. Maybe a little bias can be magnified after processes of layers. Researchers found that adding a small noise can fool neural network. Here is an example. This is the panda image. By adding a noise, we get a perturbed one. This perturbed image is indistinguishable to human eye compared with the original one. But for neural network, it can it could be classified into different class. Persons can exploit this property to do malicious attack. For example, unlock other people's phone. Imagine if you are in a self-driving car, suddenly change the light can fool the neural network, so it can lead to the car collide into wall. So finding efficient attack methods are crucial for us to understand how neural network works and avoid the dangers in reality. In this final project, we explored an attack dedicated for GCN.
Hi everyone, my name is Francie, and I'll introduce what we have done and our contributions in this project. So now my teammate has introduced what adversarial attack is, using picture as an example. Now let's see how to perform attack on graphs. So our target model is GCN, which is for node classification tasks, and our attack target is adjacency matrix, which means we try to corrupt the connections or you can see edges between nodes. And our attack goal is to make the classification results as wrong as possible by maximizing the loss of the model. And of course, there are constraints for the attack. For like, we need to limit the number of perturbed edges for the attack to be unnoticeable. Otherwise, it'd be like a complete different data. And besides, in our project, we consider conditions that are more general, more difficult. For like, we have no information about the target model for like these layers or the parameters, the structures of the model. We have no information about that. And this kind of attack is called black box attack because the target model is like a black box to you. And furthermore, we like to perform black box attack with limited number of queries. And what this means is I will introduce them later. So our contributions for this project is that we propose two methods. The first one is a black box attack, and the second one is a black box attack with limited number of queries. So let's see how we did this. So as our goal is to maximize the loss, a natural idea is using gradient ascent as opposed to gradient descent. But in our situation, we do not know the internal information of the model. So we cannot use backward propagation to obtain the gradient. Then how should we do? We naturally think about using estimated gradients. And the formula we use to estimate gradients is as shown in the slide. So what we have here is for input vector A and a random function GA. The derivative of GA with respect to the kth component AT can be approximated by this formula, which is called the symmetric difference quotient. And S in this formula is a very small constant. And this is easy to understand because it's very similar to the definition of derivative. And by using this formula, we can get the gradient of the loss function L, and with respect to the ijth element of adjacent matrix, can be approximated by the formula below. So using this, we can obtain the gradient of the loss function to every single element of adjacent matrix. So then we select the edges with top m biggest gradients and perturb those edges. M to be the number of edges to be perturbed. So this is our first method, and it's quite simple, honestly. But we know there's a problem because for this attack to perform, we need to perturb every possible edge of the target node and query the model loss to estimate the gradient. And so if the dimension of the adjacent matrix is n, then we need to query the model loss like 2 times n times. And so that is quite a lot. And in reality, that can be very cost consuming. So how to fix this problem? So we propose the next method, black box attack with limited number of queries. And before we introduce this, I would like to bring a concept called graph embeddings. And it is to map each code to a low-dimensional feature vector while preserving the connectivity by spectral decomposition. Before I go further, my team member to introduce what is spectral decomposition and how we can get graph embeddings from that.
Before going into our method, let's review the spectral decomposition. Also spectral decomposition, also called eigen decomposition. Matrix A can be decomposed into 3 matrices, the multiplication. The first matrix is constructed by juxtaposing the eigenvectors one by one, and the last one by stacking each eigenvectors row by row. The middle one is a diagonal matrix. We also can rearrange the eigenvalues from largest one to smallest one. We can also rewrite this into terms the plus. We can say the first one because the lambda 1 is the largest eigenvalue, so the first term contributed to A most, and the last term contribute little. So if we want to destroy the construct of matrix A, we would like to focus more on the first term. This decomposition is not valid for arbitrary matrices, but for a real and symmetrical matrix, we can always do it. In graph, the adjacency matrix is the real and symmetrical. So our method used this decomposition to attack GCN. Next, my teammate will introduce the relationship between the spectral decomposition and our method.
Okay, so now you know what graph embedding looks like, and how to get it from spectral decomposition. And since it is a low-dimensional feature vector, so naturally we can think of attacking the graph embedding instead of directly attacking the adjacency matrix. So that way we have less dimensions to attack, to estimate. So we only estimate gradients of the dimensions of graph embeddings with the top D highest eigenvalues. And the D is the limited number of queries. So then we perturb based on the estimated gradients on graph embeddings, just like before. And since we have the spectral decomposition formula, so there is a natural relationship between graph embeddings and adjacency matrix. So the perturbed graph embeddings can be turned into the perturbed adjacency matrix. The next final step is the same as before. We select the edges with the top and biggest perturbation, and n being the number of limited perturbations. So this is it. This is how we perform black box attack to limited queries. So let me sum up. Our contributions are we propose two methods. First is a black box attack using estimated gradients. And the second one is black box attack with limited number of queries by attacking graph embeddings. So now let my teammate to introduce our experiments and results.
Next, I will introduce the final part. To be more specific, I will show you the datasets we are using, the evaluation matrix, the baselines, the performance of our method, the analysis for both the impact of perturbation and the query, and the conclusions and the future work. We use the three datasets, Quora, SciSayer, and PubMed. All of the three datasets are academic datasets, which means each node is an academic paper. And for example, if paper A cites paper B, then there is an edge between node A and node B. And each node also has its own features. For example, title abstracts the year of publication like that, and each node also has its own label. We use misclassification rate as our evaluation matrix. In this formula, n is the number of nodes attacked. NMC is misclassified node. We expect after being attacked, the classification of the node is incorrect, which means the misclassified node is more close to n. In other words, we expect misclassification rate is more close to 1. We have three baselines. The first baseline is random tagged, which is randomly select a given number of edges of the node to add or delete edges. We also use fast gradient sign method. It is one of the earliest methods of adversarial attack. We also use bandits. It is another black box attack method against the GNNs. And here is our overall performance. We set the perturbation limit to 10, the query limit to 10, the dimensions of node embedding to 20. And we can say that our black box gradient estimation performs close to FGSM. And for core dataset, it even performs better. For embedding-based method, it performs well on Quora. For LE attack method, it performs well the SciSayer dataset, which is very close to the gradient estimation. And all of the three methods performs better than bandits. In addition, the random attack performs worse, which is very makes sense. We also analyze the impact of perturbations. The orange line shows the result of embedding-based method. The yellow line shows the result of LE attack. The green line shows the result of bandits. We can see that the result of all of the three methods increases on all the three datasets with the number of perturbation increases. And embedding-based method and LE attack both surpass the performance of bandits. We also analyze the impact of query attack effects. We can see that on Quora and PubMed dataset, the embedding-based method and the LE attack didn't increase with the number of query, but they also surpassed the bandits. In conclusion, our study introduced two black box attack methods for GCNs, and the experimental results validate the effectiveness of both the gradient estimation and the embedding-based approaches. For the future work, we could extend attacks to other GN architectures or other GN tasks. For example, we can use link prediction and graph classification. We could also develop adaptive defenses that dynamically respond to adversarial perturbations, or investigate adversarial robustness in dynamic and heterogeneous graph scenarios. Yeah, and that's all. Thank you.